Okay. So we started talking last time about random projection idea. So bring up the chat. Okay. So what we have here is, just to remind you, we talked mostly about we talked about most of the ideas. I just want to briefly recap. The idea was that we have a collection of points in RD. Let's say I have capital N, which could be in the thousands, let's say, or 100,000, and then I have RD. So the dimension of these objects, they could be images, they could be gene expression data, and that's generally big. So 10 to the 5, let's say 10 to the 6, or 10 to the 4 even. And we would like to map them to a smaller, like lower dimensional space M, such that the pairwise distances are approximately preserved. So I would like this approximation to hold. So I would like to, and then we decided to do it with a linear transformation. So I apply this linear transformation x to ui. So I get this collection x u1 up to un. And what I would like is that the difference between the two, if I take the difference, and I take the L2 norm, that would be the distance, it is close to the distance between ui and uj. And so this expression here that we had, this basically inequality, just formalizes that idea. So I have the pairwise distances squared after transformation are within a factor of 1 plus delta and 1 minus delta of the distance squared for the original data. Okay. And so the idea was that this can be done. There's this lemma called Johnson-Lindenstrass embedding, or Johnson-Lindenstrass lemma that says that this mapping can be basically taken to be a random projection, or even more simpler object would be a random Gaussian matrix, or you could even take it to be sub-Gaussian. I guess that might be one of the homework problems. So you take the matrix M by D. The entries are IID, and you normalize it by 1 over root M. This acts like a projection. It's not a projection, but it acts like an approximate identity. It's mapping from RD to RM. And so the result, the interesting fact about this, again, to recap, is that M can be taken to be of the order log n. So, and you can see the dimension of the original data does not appear here. So there is no dependence here on the dimension. Okay, and then one point I wanted to make is, so Deepesh, are you here?
Yes.
Okay, so last time Deepesh asked a question about realization, and I thought a little bit about that. So what I mentioned is that this result holds with high probability.
Yes.
So let's say in practice you want to implement this.
Yes.
There is a procedure that you can follow. So the idea is that you can generate a random Gaussian matrix. Okay, and then you can compute these things, right? So you can compute this pairwise distances, and you can also compute these pairwise distances, right? And then you can verify whether this holds, okay? And this result is saying that with probability 1 minus epsilon that holds. If it is violated, you draw another Gaussian, you verify it, and you draw another Gaussian, you verify it until you have a realization that satisfies this inequality, right?
I see.
So this idea says that rule, it's like if you have a stopping rule, that with probability 1, you're going to stop in finite steps. And then you can calculate So you can boost your probability. So if like you can say that if this is epsilon, you can compute how like what is the probability that you need more than 5 raws, and that will be much smaller, right? And the probability that you need finitely, like after a finite number of tries, you win, that would be 1, okay? So there is an algorithm based on this that you can implement. And there's some guarantees on the fact that that algorithm stops.
One question. I didn't understand. How do you do probability amplification here? I didn't get it.
So the thing is, this is like a geometric, so you have a procedure that has probability 1 minus epsilon of success, epsilon probability of failure.
Oh,
right? So
okay.
you repeat it
Got it.
until
Got it.
That would be a geometric series, and the probability sort of gets better, right? So
yeah, but that depends on your data set, right? Your vectors, your points.
So these guarantees that I'm pointing out here, they don't depend. So they hold for any sets of points. That's the idea here, right? So you can see the M here does not depend. Nothing in this result depends on the U's, right?
No, but when you do a union bound, that says that you are only doing it for these, only doing it for n points, right? But
right, but for this
n
specific
points, yes, right. yes.
But your points are fixed, right? So you fix your points, U1 up to UN.
Oh, okay.
And so this is saying that with this probability, this is going to hold. So if you repeat it multiple times, you get better, right?
I see.
Right,
yeah.
Just think about this. There is a procedure to implement this. And
yeah.
It's like simple, right?
If your points are fixed, then yes, then I agree. Yes. But if your points are not fixed and you want to give a general thing, then yeah, that's what I was asking actually.
No, yes. So yeah, if you want to do it for that, that's probably not, you can't have a uniform. It's not going to be uniform. But it's not going to be, there exists a matrix that works for every year. Yes, that would be so difficult. Yes.
Okay.
Good.
Okay.
Good. Okay. So other questions maybe before? Okay. So now let's recap what the argument was. So the argument is that you start from a tail bound, and the tail bound is just for these. So you pick one specific UI, let's say, and uj, fix that, and then you have I want to control this quantity, and this is x times ui minus uj. So if I call ui minus uj some u, and then I would sort of replace x with z, so I get 1 over m z times u norm squared. So this is the basic object that I have to control. The idea is that this object is going to be sub-exponential. So how do we show that this is sub-exponential? I have some sort of argument there, but anyone? So let's not look at this, maybe do it. Let's say for the people who haven't looked at the proof, how do you do this? No. I'm gonna do like another page here. So let's say if you want to do this on your own, how would you proceed? So can you give me a tail bound for this guy? So Z is a Gaussian matrix. So what would be the distribution of what would be the distribution of ZU? Anyone?
All the entries of this will be Gaussian, independent. Yes. Gaussian, and because they are sum of independent Gaussians, so entries will be independent Gaussian.
Right. So one way to see it is that this is a linear transformation of Gaussian, or not linear transformation, but yeah. So if you think of the z's, let's say z1 transpose, let's say up to z m transpose, these are the rows.
Yes.
Right. Z times u would be z1 transpose u up to zm transpose u. And then you can verify that individually they're Gaussian, they're standard Gaussians, and the covariance of pairwise covariances is covariance of this guy and this guy, let's say. Sorry, let's do like I and j.
0.
Right, so this would be the expectation. Now you could write it like, do the trick. So u trans, I can write it as this times zj transpose u. Sorry, yes, so that's, and this is going to be u transpose expectation of this. And these are independent, so this is going to be 0. So the covariance is 0, so this turns out to be, and this is also 0, and it turns out to be 0, and then covariance is also identity. Okay. So what is the distribution of this guy then?
It would be chi squared because the sum
Exponential.
of independent.
Right. Chi squared. Who said chi squared? Can you say that again?
It's chi squared because it's like the sum of squared Gaussian variables.
Yes. Who was talking? So see if I can. Ian, is that?
That was me, Ian, yeah.
Yes. Okay. So chi squared m minus 1, yes. So we had a result about chi squared, right? So I can now use this result, which I had here, right? Say sub chi squared or sub exponential, and if I restrict t, it's going to be next sub Gaussian too. Was there a question?
Yeah, I didn't get it. Why is this chi square m minus 1?
Right, not m minus 1, chi squared m. Does that look better?
Still not.
It's not? So
why is this?
So yeah, and why is that?
So like the L2 norm is equal to like the square root of the sum of the variables. So therefore,
right,
the L2 norm squared would just be the sum of the variable squared. So the sum of zu squared or zi u squared, which would correspond to, as we just proved, that's distributed normally with mean 0 and covariance IM, and the sum of squared normal variables that are independent corresponds to a chi-squared distribution.
Yes, that's basically it. So if you call this x.
Okay. So I got it. Yeah, so this is because your u is a unit vector. No?
Oh, you're right. Okay, so this is not going to be chi-squared. So that's your question. Okay.
Yeah, so if it is a unit vector, then yes.
I see. Okay. Yes. So this wasn't quite correct. So let's do something else. Right. I see the point. So if we do, so there's something wrong here. So Ian is correct, but what we did here is not correct. So the thing is, what is the variance of this? Variance of the I transpose U. Anyone?
A 1?
No.
No.
So the variance of this is going to be this.
Yeah, but this is 1. Okay, so I assume that.
Yes, not 1. Okay. So we have to fix this.
Yes.
just verify that for yourself. That shouldn't be difficult. So this is going to be like this. So everyone is okay with this variance of this being, try this out. So basically you go through this, you would get zi transpose here, that would be I identity. So you get U transpose U in that case. So then if I define X to be ZU divided by norm ZU, that would be what? What is the distribution of this guy? Anyone? Oh, sorry, not this one. That would be difficult. Can't see the silence. How about this? What is the distribution of that?
Would just be a standard normal.
Yes, so that would be standard normal because we are normalizing. It's not, yeah, it's strict standard normal vector or canonical Gaussian. So if you normalize it, you divide the covariance by.
Yes. Yes.
So now the norm of this is going to be chi squared. Is that correct?
Yes.
Okay, then I can use this result that I had. So basically saying that the probability that 1 over m norm of x squared minus 1 is bigger than t is less than or equal e to the negative, let's see.
T square m by 8.
Yes, I'm applying this. This is going to be my x squared, right?
Mm.
And so I would get, to make this, I would get make 2 times e to the negative mt squared over 8. Sorry, I can't remember. Loss of short-term memory. So 2 mt squared over 8.
Yes.
Okay.
Yes.
So what does this give us? This, if I do the, so if you do this, I get, this is just going to be 1 over m ZU squared divided by U squared, right? Minus 1 bigger than t, dot, dot, dot. Found is the same. Correct?
Yes.
And then 1 over m times z is x, so this is just going to be xu. This is my x, the capital X.
1 over square root of m times z. Yes.
Right, right. But yeah, z over root, yeah.
Yeah.
But this is still correct. So I get minus squared u squared t. That's not equal to. Right.
Yes.
So we're almost done. I guess this is what I have here. Yeah, I could have let it there. Yeah, so put a delta here. Delta, delta. Same idea. So I can apply this to, this holds for any u within a similarly norm constraint. So I get probability that basically xui minus uj is different from this, bigger than or equal to. Maybe I should have kept it that way. That would have been easier. Just let's keep it that way instead of writing everything. So I get this divided by u squared minus 1 bigger than delta. This probability is less than that. And then what I have is I apply it to ui minus uj. And then I get uj squared minus 1 bigger than delta. This is less than the same thing. Okay, so this holds for any fixed I and j, as long as ui is not equal to s, so I is not equal to j. Otherwise, I'm dividing by 0. Okay, this makes sense to people?
Yes.
Yes, to everyone. So what is the final step? So this inequality that I have here is basically this inequality. So if you divide both sides by this guy and then subtract 1, and that would be equivalent to this expression. So this is the inequality there. The complement of that inequality, basically. The negation of that inequality. Okay. So I want to show that the negative statement has small probability. So what is the final step?
Union bound.
Right.
Triangle inequality.
Triangle inequality. Who said that? That was a new voice.
This is Jia.
Jiayi. Okay. Triangle inequality. So what kind of triangle inequality you want to use?
Like, because we want this to hold for all pairs I and j.
Yes.
So we can add them up on the right hand side. Like add up the probability for every single pair. And that would be like a upper bound.
Right. So okay. So that's the union bound that was sort of, that's the name is union bound. That's the same idea. Right. So basically the probability that let's say that these are generalized statements. So let's say I have a function which depends on, let's say, ij. So I and j. So the probability that this is bigger than t is less than, let's say, I don't know, g of t. Okay. I want to say that what is the probability that supremum over, let's say, I not equal to j is a maximum. If I and j bigger than t, this would be the probability that the union of these events hold. F and j bigger than t, I not equal to j. So the maximum is going to be bigger than t if at least one of these terms is bigger than t. So that would be a union. Okay, so this event is the same as this event. And so the union of a bunch of events is the probability is bounded by the sum. So this is bounded by the sum over I not equal to j. Any single one of them bigger than t. And I have a uniform bound on this. So this is going to be bounded by g of t. So what I would get here is that this is going to be bounded by n choose 2. Let's say there are n of them, times g of t. Okay, so that's the idea of a union bound, which is generally done. It's good to remember the name, right? So everyone happy with that? If you have a question, let me know. But this is basically the final step. So I would add it like a soup here. So that will sort of save some time. I'm going to just do it here. So I'm going to add a max over I not equal to j, and then I pay a price, which is this here. N choose 2. I have my 2 here. Okay, so I have this bound now uniform. So this is a uniform bound. Uniform over all pairs. So the difference what is the difference between this bound and the bound that we had before? What is the difference between the two?
The other one you can only apply to certain pairs, but this one you can set as a set constant for all of them.
Yeah, so basically the previous one holds for any pair. So for any pair, that particular event holds with that probability bounded by that. But this is saying that this union of these events, or basically this uniform event, holds with a certain probability, which is a much stronger result. Okay, so this is saying that to guarantee that basically none of them is bigger than delta, that would be the complement of this event. I will have that the probability 1 minus n choose 2 times that. Whereas to have any single one of them, any particular one of them bigger than delta, I could have it with larger probability. In any case, okay, so this is a uniform bound. So what is the final step? I want this other side to be bounded by, I want this to be bounded by epsilon, yes. So I would actually further bound this by, I think, I could bound this by n squared. Let's go to the downstairs here. Yeah, so you could just bound 2 times this by, so that's the same bound. Maximum being bigger than delta is equivalent to saying that this holds for some pair. So this is the same as saying maximum over I not equal to j, blah, 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 bigger than delta. So I'm going to use this. And so I'm going to set this side less than epsilon. So that's this object here. And then you can do some little algebra to show that. Basically taking n large enough, you can make this small enough, right? So this is polynomial in n, and taking m to be log of n properly, or root log n, sorry, root log n properly scaled, you get the result. Just show that this inequality holds if this condition is met. Okay, so that completes the proof. Questions? No questions? All good. So the same argument can be done for a general sub-Gaussian matrix. So the only thing that you have to supply is this tail bound here. And you can use the general sub-Gaussian calculation and sub-exponential. So sub-Gaussian is the square root of sub-exponentials. So we use the specific tail bound for chi-squared variables because we started with Gaussians. But you can have the same result for any sub-Gaussian distribution, and that's a problem in your homework. So you could use the general machinery, let's say the HTP approach, to get a bound up to constants, which looks similar. Okay, there's nothing special about the Gaussian here, except the constant. Okay, no question about the Johnson and Strauss. Okay, so let's move on then. So the next result is, it's another application. Is about the norm of sub-Gaussian vectors. And this is a result in the HTP book. And it's a very interesting result. I'm not going to prove it. The proof is interesting, but uses similar ideas and a little bit of a trick. I just want to point out that the result sort of follows from similar concentration inequalities. And I encourage you to go read the proof, just give you the idea. So suppose you have a random vector with independent entries, and these are sub-Gaussian. So each coordinate is a sub-Gaussian random variable. and they're independent, and each one satisfies this sort of normalization constraint. So the second moment is 1. Okay, so if the second moment is 1, if I look at this L2 norm, and if I take the expectation of this squared, what would this be?
N.
Yeah, so this is going to be the expectation of the sum of squares, and so this would be N. So you would guess that, so what would be bound on the expectation of this guy?
Upper bounded by square root of N.
Yes, why?
Just by because we know that, I mean, Jensen's.
Yes, by Jensen's inequality, that would be the case. So this is bounded by, can verify root expectation of this, which is root N. So that's the Jensen's inequality, right? Applied to the square root. Or you could do it with x squared. It's okay either way. This result is showing that in fact the expectation, or this norm is concentrated near root N. Not only it's bounded by root N, but it's very sharply concentrated near root N. So this is saying that if you look at the norm and then subtract the root N, which is not the exact expectation, by the way, but the result is saying that this is going to be sub-Gaussian, and the sub-Gaussian norm is bounded by k squared, where k is the maximum sub-Gaussian norm of these vectors. Sorry, these elements of this vector. Okay, so if this k is a constant, then this is going to be a constant. Okay, so you can see this is growing like root N. If this is a constant, this means that the norm itself is very sharply concentrated around root N. Yeah, so it shows that the norm is highly concentrated. This is not correct, but highly concentrated around root N for large N with high probability. In particular, if k is O of 1, it's a constant, bounded by constant with high probability, this norm is going to be root N plus minus something which is constant. Another way of saying that, if you go back to the tail bound, so this bound on the norm, sub-Gaussian norm translates to a tail bound on this object, so on this deviation. So you can say that probability, so this translates to the probability that this norm minus root N is bigger than t is less than or equal to some constant e negative, another constant, let's say c1, k squared, t squared. Sorry, not this one, the other way around. Divided by the norm, basically. So divided by the sub-Gaussian norm. Minus, let's say c1, let's say c1, yeah, constants get out of hand. So this is going to be less than or equal to, let's say c1 e to the negative, let's say c2 t squared over k squared, absorbing constants into each other, right? Or I could replace t with k times t, and I get, sorry, this would be k4. Because the sub-Gaussian norm appears here squared. So I get something like this, case to the 4. Okay. And if I replace t, so replace t with k squared t, then you'd get this result that this norm is going to be root N plus minus k squared times t with probability, which is 1 minus e to the negative. You probably have to have a 2 here. I believe I can put a 2 here. That would be okay. Something like this should hold. Okay. So what this result is saying, you can figure out the details from the sub-Gaussian tail bounds. What this result is saying is that, let's say in R2, so I have a circle, let's say, of radius. I'm gonna plot it in R2, but the idea is that you have to view it as a n-dimensional plot. So this would be the sphere of, just think of it as a sphere of radius root n. And the sub-Gaussian vector is going to have a norm which is within a shell of constant radius around this. So the norm of this is going to be this. So the vector can be here. Okay, not near the origin. Okay, and you can imagine the root n. So n grows to infinity. The dimension becomes bigger, but this shell, the size of the shell doesn't change. So you can see that the concentration is very interesting. So it's dimension independent, which might be very surprising at first. So a sub-Gaussian random vector of independent coordinates, it's random, but not in terms of its norm. So its norm is very sharply concentrated. So the direction is sort of random, but for example, you know that with high probability, it's not going to be found near the origin. It's going to be very much found near the, and that's sort of partly because you normalize it like this, because of this normalization. Okay, is the idea of the result clear?
Yes.
Yes.
So instead, if you have expectation of xi squared to be something other than 1, how will your bounds change?
That's a good question.
I think instead of square root n, you will get whatever the bound is, right? Because that one is corresponding to the radius in scalar case, and that leads to the square root of n, right?
Right. So the advantage of this result is it gives you a concrete number, like bound on the norm. If generally, if this is not, if they're normalized, not normalized, then yes, you would be close to the expectation of the norm of
Yes.
x, which is whatever it is, right?
I see.
Yes.
Okay.
But the general idea is that you care about the scaling, and for example, if the variances are not, my guess is that you can show, for example, if the variances are bounded, let's say, from above and below, let's say, then the scale is still going to be root n. But let's say if you have a bunch of them that have variances that are going to 0, let's say, as the size grows. So if the expectation of xi depends on n as n grows, then things would be different.
Yes.
Right.
Yes.
Right. These type of results are all about the scaling. It's good to remember this is scaling. This is roughly the scaling where, in cases where the expectation of xi squared are constants, basically. Okay, it doesn't matter what constant, but as long as they're within the same sort of constants of each other. Okay, one is like 1, the other is 2, and sort of something like that. Okay. Then the scale would be root n. Otherwise, the scale would be different. David is saying, so can you say that, your comment loudly?
Well, the question was, what if exi squared is something else, right? But couldn't you just divide out by a constant to make it 1, and then you'll get basically the same result with an extra factor outside?
I could do that, but then I wouldn't get the norm of x. So let's say if I had expectation. So let's say expectation of xi squared was, I don't know, alpha I. squared, let's say. So you'd say divide xi by alpha I, right? Then this would be norm 1. Then this result would tell me something about the norm of this vector, x1 divided by alpha 1 to x1 divided by alpha n. This minus root n would have the same property. But that's not what I want, right? If you care about the norm of x, the norm of this vector is different than the norm of x. Does that make sense?
Yeah.
Right. Yeah, it's in general tricky because you could have, so let's say one of these entries could have, let's say expectation of, let's say x1 squared is close to 1. The rest are very small, almost 0. And the norm would be close to 1. Okay, so it's not going to be close to root n. So this takes like one of the sources of variability out of the question, and then there's a clean result. Okay.
So are you assuming that xi's are independent here or not?
Yes, you're assuming independence.
Right. Okay.
Yes, that's key.
Okay.
Okay. Okay. So I'm going to give you a simple heuristic sort of explanation, and then the proof we can read. I have it here, and it's also in the HDFE book. It's basically the reverse of the things that you do usually. So you first come up with a bound on the squared norm, which is of the form, has the sub-Gaussian form, and then you translate it to a bound on the norm itself. And there's a little bit of a trick there, inequality and sort of, but this is basically saying the squared norm is sub-Gaussian, then the root of it is going to be exponential, sub-exponential. And this is a nice trick to see, in terms of the tail bounds. Usually you don't see it in terms of tail bounds, but we can get from a tail bound which is sub-exponential to a tail bound which is sub-Gaussian by taking the square root of the variable. And this sort of argument gives you a way of doing that in the tail bound, let's say, domain. But let me give you the simple argument. The simple argument is that this is going to be n. We did this calculation above here. So what is the variance of this? The claim is that the variance of this is n times the variance of one of them. Why is that?
Independent and all are
right.
bounded by. I mean, you need a mean to be 0 here, right?
No.
Or otherwise, no. Why is x1?
So this is going to be the variance of the sum I from 1 to n xi squared. And xi squared are independent, so this is going to be the sum of the variances.
Right? Yes.
And they are.
Why it is only 1? Why?
You're right. Okay, so they're here. I'm assuming that they're in like I'm assuming that they have the same. Yeah, for this simple argument, I'm assuming that they have similar mean. This is not going to be otherwise. So I'm assuming, let's say, IID here. Right. Yes. So this is going to be n times variance of.
Yes.
But this is not needed for the result, just for simplicity. Because we're doing a heuristic argument, let's do that simplification. So then it would be n times the variance of one of them. So variance of this guy squared. Okay. So this quantity has variance of the order n. This quantity has mean of the order n, variance of the order n still. Let's say the variance of these, one of them is constant. And so the standard deviation would be of the order root n. Okay, and the standard deviation is of a lower order than the expectation, so you have concentration. So you have some random variable, basically this guy, has mean of some order and the standard deviation of a lower order, this thing concentrates. And so, for example, you can show that this is basically what you'd say is this result roughly says with high probability this guy is going to be approximately n plus minus O of root n. That's what this little calculation shows with high probability. And then I take a square root, I get that this roughly root n plus minus O of root n. And then you can verify that this turns out to be this. So if you do a Taylor expansion of roots basically this here. So this might not be obvious, but this is an interesting thing. So if you take the square root of 1 plus t, and if you do Taylor expansion, it would be 1 plus O of t. So it would be, so apply to this guy, so it would be 1 plus O of root n, and then multiply by root n. So you get this result. This is somewhat of an interesting observation. And you can also read this side note here. So if you do a, people often do this inequality. If you do this inequality, you get a worse bound. So this is a sharp bound. So if you take a square root of something which is n plus minus O of root n, you get root n plus minus O of 1. And that's basically the general idea. Okay. Does that make sense? Does it make sense? Yes. So this little thing here is basically these concentration bounds. So once you have that, then so you can formalize that. But it's good, generally good as an advice. Let's say if you want to prove things, if you can do a calculation of the mean and the variance, it sort of helps you a lot before you try to get down into the technical details. If you want to prove something is concentrated, and if you have, usually you need to have some sort of a handle on the expectation, or if you can subtract the expectation. You don't need to know the expectation, but if you look at the deviation, basically, you would like to say that my variance or the standard deviation is of the lower order than the variance. If your, standard deviation is of a lower order than the expectation, then the random variable sharply concentrates around its expectation.
So one question, are you assuming that SD of x1 square is constant?
Yes, I'm basically assuming this thing is.
Okay.
This is
order 1, right?
Right, order 1, yes.
Okay.
Yeah, this is also assuming that IIDness, but you don't need the IID fact to go through the argument. But this is just for to know. Other questions about this? This is just good to remember. So if you have independent sub-Gaussian variables, and if you normalize them to moment being 1, to their moments being 1, then the norm of that vector is sharply concentrated around root n. This gives you a very rule of the thumb to work with random vectors. Okay. No questions? So one question would be, what about other norms? So this was the L2 norm. So I'm going to be very sharply concentrated near a constant. How about, let's say, the L infinity norm? So what is the L infinity norm? So that's the L infinity norm. The L infinity norm of a vector is the maximum of the absolute value of the elements. So suppose I have the similar setup. I have a vector with independent sub-Gaussian entries. Anyone knows what the order of the infinity norm would be?
Can you please repeat it, please?
Sorry?
Can you please repeat what you just asked?
You mean write it down? I didn't get that. What do you want me to do?
Just repeat, please.
Oh, repeat. Okay.
What
So
you just asked? I missed it.
Right, x1 up to x. So entries are sub-Gaussian. Let's say the sub-Gaussian norm. So yes. Actually, I don't need independence here.
Okay.
Sub-Gaussian. And then the psi2 norm is bounded by k for all I. Then what can we say about the infinity norm here? So I see a Honda. So can you say it loud or?
I was thinking this is an extreme value, which may scale as log n.
Okay, it's very close. There is a little bit of modification that you have to do. So how do you know how to drive a result like that? Any idea how to do it? It's close. Log n is close. It's going to be logarithmic, more or less. So where did you see this, and in what context did you? I'm curious.
I'm sorry, I'm not clear about that.
Okay. Anyone has an idea of how to show a bound on this? Let's say I want to prove a bound. I want a tail bound on this guy.
Are we going to use the union bound again?
Right, I can use the union bound. So I could do.
Yeah, but then it will be a probabilistic statement, not a deterministic statement, right?
It is not, so we're doing probability here. Nothing is deterministic in this course.
Oh,
okay. Right. So Gaussianity is a probability, probabilistic property. So that would be this. So union bound would give you what? Less than or equal to n times the probability, I would say, maximum probability of one of them. So if you have a bound on the probability of one of them, uniform bound, right? Then you would get this. So what is the bound on? So I need to assume something here. So I'm going to assume that these are zero, right? So suppose
e to the minus.
So zero mean.
Yes,
so
so it would be so this will be bounded by 2n e to the minus t square by k square.
Right. Each one would be, let's say, e to the negative, let's say some constant t squared over k squared.
2 times.
And so the whole thing would be bounded by 2n e to the negative c t squared over k squared. Something like that. Right?
Yes. Okay. And I see. So
let's say I want some statement which holds the probability 1 minus delta, let's say, or 1 minus epsilon. Or 1 minus, I don't know, gamma. Or...
Yeah. So this is equal to, if you can take n to the exponent, this will be equal to 2e to the log n minus ct square by k square.
Right, so this would be x log n minus ct squared over k squared.
Yes, and and now you can take the minus of the whole thing, I mean, right? And then that will give you
right. The trick generally here is that I would do something like this. I'll try to kill the log enter. Okay, so
yes.
So I would like to kill this term. right? This is negative, so I can make, so this is growing, so log n is growing to infinity. I would like to get rid of that. I'm going to take t as small as possible, but big enough so that I can kill the log n. And so you can verify that I can take it to be, so if I take this to be root,
log n,
let's say some constant, c2 k, let's say do it like this. I want to do it, I'm going to do, right, let's do, because my result is about, with proper constant, let's forget about this. Let's do it with the size of Gaussian norm. But so this could do, I could do, for example, let's say I could do it with, what can I do?
I mean, you want t to be bigger than k times root log n.
Let's say I could do, for example, let's say I want this to be like this.
Yes.
Okay. Then what I would get is that t would be what? T would be
1 plus gamma times k square log n by c to the whole square root.
Yes, k squared by
c log
n, then
whole
the
square
root.
Yes.
Right. So if I take t to be this, then what I would get is that this side is going to be bounded by 2, or actually it would be equal to this minus gamma log n. Right. And so it would be 2 to n to the negative gamma. So say if gamma positive, this is going to go to 0.01. Right. So it gives me a high probability bound. So what I've shown is that if you plug this in t here, so t, what I've shown is, let's go down here. So what you've shown is, come here, probability that this is bigger than root 1 plus gamma k squared over c log n is less than or equal to 2 to the negative gamma. Or with probability bigger than 1 minus 2 n gamma. We have the complement. So x infinity is less than, up to a constant that c is a constant would be k root 1 plus gamma log n.
Square root of log n. Yes.
Right. So the order, the key is that the order is of the order square root log n. So the infinity norm scales like square root log n. Here's another way of writing it. This sigma is substitute for k. So I did it with a sub-Gaussian norm, but here in this lemma, I'm doing it with sub-Gaussian parameter. So you get explicit constants here. But the thing is, so this is going to be the maximum of the sub-Gaussian parameter. So just look at the lemma 5, and the proof is basically the same, but it uses using the alternative characterization. The main point is that, yes, the main point is that this sub-Gaussian norm is scaling like root log n.
I mean, that root log n is the, I mean, it's a, so you got this root log n because your probability of error is this inverse polynomial. If you want to get something else, you will get something else here, right? If you want to get a probability of error which is exponentially small, you will get t to be square root of n, right?
Right, but the issue is, yeah, so let's say I want something which holds a probability with high probability in a sense, okay? let's say the smallest that you want, let's say the probability to go to 0. You want a statement that holds the probability that goes to, 1. Right? Then that would be an overkill. So doing it at exponential, yes. So that would be true if you need it. But what we are saying, let's say the order is whatever holds with probability that goes to 1, let's say. Okay, the smallest thing that you can put there is still the probability be going to.
Yeah, but then you can also take like 1 over log n. That also goes to
1
0.
over log n?
Yes. I mean, instead of getting 1 over n to the gamma, you can get 1 over order of log n. That is
right.
a bound of t which scales as square root of log n.
No, it can't be log n.
I think.
No, if you take this, so you want to take t to be, so you want to say this, I can take it to be 1 over log n here, right?
Yes.
To the gamma.
I mean, some constant here
right,
and
try
there.
it.
And
you shouldn't be able to say that this is log n.
I see.
You can't do it.
So? I see.
Log n is too small.
I see.
Right, so if you plug in something log n here, it's going to be eventually, log n is going to eventually kill it.
Oh,
right?
yes.
So it's not that
yes,
obvious.
true. Yes, true.
Think
true.
about this, yes.
Yeah, true.
Another way of doing it is, you can also, if you worried about the probability bounds, another way is to try to control the expectation. I think we have it in Howard problems or some else. Try to control this. There's no probability there. And then you can show that this is going to scale like sigma root log n. I think that's in one of your homework problems.
I see.
That makes it more clear. So the expectation is going to scale like sigma root log n. So this is the right order.
I see.
But it's a good question.
Got it.
Okay.
Yeah, because that is the most of the probability is there. That's the inverse polynomial, right?
Yes, so you can't sort of
got it.
do much. Yeah. Even if I want to do it like less than 0.99, this is the best that I can do. Even if you want it to be a constant.
I see.
Sorry, that's a 0.01. I want to do it with 1 minus epsilon. Epsilon. Epsilon being constant, that's, let's say fixed epsilon, but epsilon sufficiently small, so they have to pay a log n price, root log n. Okay, so we have a question here. No problem. Do you want to ask your question yourself,
Sure.
Zach? Yes.
Yeah. Just where you wrote probability infinity norm greater than t is it?
Oh, yes. So you're talking about this step, okay. Right?
Yes.
Yeah, so what I want to say is, generally what you would do is, this is an application of the union bound. Let's see if we have a place here to write. I would do this step here. So what you end up doing is, so you see the first one, right? So this is the case, right? This is equality.
Yes.
Right, and then I would like to control probability of max over j, xj bigger than t. So there are these couple of steps that you usually do it in your head, or you just do it in one step after doing it so many times. This is, in your head, you do this. Maximum of this is like the union of these events. Does that make sense? That is saying that the maximum being bigger than t is equivalent to at least one of them, and at least one of them translates to union. And then you say this is bounded by summation, this is the union bound. Union bound. And then this you can say it's just a bunch of, I'm adding a bunch of numbers, right? So the sum is bounded by n times the maximum of these elements. It's just a deterministic result.
Okay. Okay.
Usually you don't do this. Usually you just have a uniform bound in this. This is saying, but this is true. Does that make sense?
Yeah.
So it's saying a sum of a bunch of numbers is less than n times the maximum of that bunch. Usually you have a uniform bound on this, like something like this. That doesn't depend on j. So we have a bound like this that doesn't depend on j, so you just replace it there at that step. But if you don't want to do it, this is how you can write it and be correct.
Okay. Thank you.
No problem. Other
And
questions?
Do you actually get more mileage out of this than by saying less than or equal to like 1 minus the probability that they're all less than or equal to t, and then that? I mean,
oh, you mean? Yeah. So the thing is that, okay. So you want to do this is, you want to say this is actually
it's equal to that.
1 minus your probability that the intersection is, right?
Yeah. Do you get
So
mileage out of that or no?
this is a good bound. This is like not the bound at this point. This is an exact expression. This is going to be useful if these are independent. Okay. So if they're independent, then you'd get the probability 1 minus basically product, right?
Yeah.
But if things are not independent, then this is not very useful.
Shouldn't you have probability of the intersection xj is less than equal to t instead of bigger than t? With
Right.
negation
Yes.
of the whole thing.
Right. So if you want to do it, yeah, properly, you have to do this. Yeah, the complement of that event is the intersection of the complements of it. So it would be this. So you have to have independence, let's say, to get something useful out of this, at least. Right?
Yeah.
And controlling this would be difficult because you would expect, what you're expecting is that this guy is small. Okay. And so in this calculation, you have to show that this is very close to 1. Right?
Or close to 0.
No, because you want to show that.
Oh, yeah.
You want to show that this is close to 0.
Yeah.
This is 1 minus, so you have to show that it's close to 1.
Yeah.
And your job would be a little bit more tricky. It could be doable if, because the probabilities are usually not equal to 1. They're generally less than 1. And if things are independent, you get products of probabilities, and products of a bunch of things that are less than 1 is usually more or less than 1.
Mm-hmm.
This usually is good if you want to establish that this thing is basically bounded away from 1, actually. So let's say if this thing is very small, then you have shown that that probability is bounded away. So this would be bigger than, say, 1 minus something is small. So you would say that the t that works in that case would be, so it would be the opposite statement. Okay, so it would be a small deviation bound. So you want to find a t such that the probability that the maximum of xj is bigger than t holds with high probability. So how small I need to take t such that I'm sure that the maximum is bigger than that. Okay, so if you want to basically prove a lower bound on this, here we're doing like, we are showing that this is of the order sigma root log n. If you want to show that this is bigger than or equal to sigma root log n as well. Okay, if you want to show this one, then what you would like to do is that I would like to take this to be some constant times root log n, and then I want to make sure that the probability that this holds is also close to 1. Okay, and then that alternative argument would work, right? But in general, it's going to be tricky.
Thank you.
I think that would be an interesting question to actually post as a homework problem. Maybe it's one of our homework problems. So let's say you can assume that things are, to show that this can't be this is the right order, you can give examples that this holds. An example would be a Gaussian vector with independent entries. Okay, then you can try to show using that argument that this has to be bigger than or equal to a constant times root log n. And that shows that in general, this bound that you found cannot be improved. Maybe I should assign that as a homework problem. That's actually a good. It's part of your homework problems in the book, but this is another interesting. I'll try to think if I can assign it. But that was a good question. Okay.
Is it more useful to find a tail bound or than a lower bound?
Who's talking? Oh, Xiaoming. Is that you?
Yeah.
Okay. So what was the question?
I am wondering if it's more important to provide a tail bound like in the previous section than the lower bound that we're just talking about. Yeah, it's just the thing we're talking about.
Right. So the thing is that you have to see what you want to prove. Here, what I want to prove is, so this result, lemma 5, is showing that, so lemma 5 says that with high probability, this guy is less than or equal to up to constant sigma root log n. That's what we have proved. Right. In order to prove this, I have to show that the probability that this is bigger than this is small. Right. I could be interested in proving the other way. So I might be interested in showing that also this guy is bigger than or equal to sigma root log n up to constant with high probability. This in general is not going to be true. We're out of time, but anyone can give me an example of a vector whose maximum is not going to scale like this. And note that I'm not assuming independence.
Only right? One entry is n and the other is
right.
Constant
right. You could have like constant vector would do, yes. Well, yeah. Or let's say you have like one of the entries, right? Repeated, for example, right? So you could have like 0 mean x1 is there, and then x1, 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 okay? And the maximum would be just the absolute value of x1, which is not scaling out root value, okay? So this is not gonna hold, the lower bound is not gonna hold in general, but let's say if I assume further that they're independent, then I might be able to show this. I'd be able to show that.
I mean, how do you show that if it is independent? You can say the X is a bounded random variable and takes IID copies of that. Even that will be just constant, right? Infinity norm of that.
Right. I was trying to do Gaussian. So what I was saying is that there exists of Gaussian variables such that this grows like root log n. Yes, I'm not saying that it's going to always. Yeah.
I see.
Right, but I'm not sure if I answered your question, Xiaomi. Depends on what you're trying to prove, which way the bound is.
Yeah, I know it. Thank you.
No problem. Yeah, so you have to first see the statement and then try to argue the right tail bound. Okay, we're out of time. Any other questions? This upper bound shows. Is that a question, Zach? Shows concentration. So this bound doesn't show concentration. This is just showing that it's like a deviation bound. It just shows that the infinity norm does not grow faster than the root log n. It's just comparing it with, this is concentration. This is saying that the two norms concentrate around root n, and this requires independence. The result that I was talking about, the infinity norm, is weaker. So it requires like a weaker assumption. And then the result is also weaker because it just shows that the infinity cannot grow faster than root log n. But this is very useful. It's just saying that you shouldn't expect the infinity norm to grow much faster than root log n. And this is basically the basic idea behind most of these high-dimensional arguments. So the infinity norm of a sub-Gaussian vector does not grow that fast. Like in dimension or in the number of variables, it's much slower than, let's say, the L2 norm. And we'll see. So this kind of lemma 5 is the cornerstone of most of these non-asymptotic consistency results. Yeah, but it's not formally a concentration result. It's just a deviation now. Okay. Any other questions? Okay, if not, let's just stop here. And please go and answer the poll. And that's it. Okay, so see you hopefully on Wednesday. Okay.
Thank you.
Thank you very much.
No problem. No problem. Bye-bye.
Bye.